In this module, we will discuss wave propagation inside that of an imperfect dielectric and wave propagation inside a good conductor. Wave propagation in good conductor will lead us to discussion about skin effect, something that is very important at high frequency wave propagation. Waves in imperfect dielectrics is something that we would actually see when you drive a capacitor with a high frequency signal, but then the insulator that is filling the material between the capacitor plates is not perfect. So if the material filling the capacitor plates is not perfect, then there is a possibility that there will be some leakage current from one plate of the capacitor to the other plate of the capacitor, leading to losses in the form of dissipation of heat inside that of that imperfect dielectric. Okay, so we will like to see what happens to this loss, or how would one calculate this loss, which is actually material constant dependent, as well as what is meant by skin depth or what is meant by skin effect when we consider wave propagation inside a good conductor. Okay, so we begin as usual that we began for the case of a lossless or a perfect dielectric wave propagation. So we begin with Faraday's law and Ampere Maxwell law. So Faraday's law is straightforward. Curl of electric field is given by minus j omega mu h. Clearly the way I have been writing this equation implies that I am assuming that the time dependence of all the field quantities in this wave propagation would all be in the form of e to the power j omega t. So because of this, I can actually suppress the time notation and realize that del by del t can be replaced by j omega. So with this assumed time dependence, then Faraday's law becomes curl of electric field being equal to minus j omega mu into h. Okay. So although I am writing mu here, in most cases we will be interested only with mu is equal to mu 0. That is, we will be interested in the cases where the material medium is explicitly not magnetic. Okay. So we will not look at wave propagation inside a magnetic material. That is something that is beyond the scope of this particular course. So although we write mu, what you should realize that mu is equal to mu 0. Okay. So with this becomes Faraday's law, and then what happens to Ampere Maxwell law? Ampere Maxwell law is curl of H is equal to J plus J omega epsilon E, right. Now in the case of a lossless wave propagation, that is propagation inside a lossless material or a perfect dielectric, we assume J is equal to 0, right. So J is equal to 0 for a perfect dielectric, okay, because there was no possibility of having any conduction charges free, so that they would constitute to a conduction current density J. However, inside that of an imperfect dielectric, we cannot assume J is equal to 0, because if we assume that, then there is nothing different from the lossless case, and we will not be able to capture the fact that an imperfect dielectric can actually conduct some amount of electricity. No doubt that electricity will be small, but it can conduct some amount of electricity in the form of a leakage current. So in order to take that imperfect dielectric into account, we let J be non-zero. So J is non-zero for a imperfect dielectric. Okay. This situation of J not equal to 0 will also describe equivalently the good conducting medium, such as a metal, right. So in a metal you will find lot of conduction electrons, therefore J vector, the conduction current density, will be very high, or will be at least quite appreciable compared to the displacement current in a good conductor. On the other hand, if the medium is imperfect dielectric mainly, then conduction current will be there, but it will be very small in magnitude. Okay. In any other medium, the relative magnitudes of conduction current and displacement current determines whether that medium can be considered as an imperfect dielectric or as a good conductor. Okay. So in any case, we will assume that J is non-zero in order to capture both the imperfect dielectric as well as good conductor effects. So we have J non-zero, but we also invoke the fact that J is linearly proportional to electric field in the form of Ohm's law, right. For the field expressions that we described earlier, J was equal to sigma times E, except in this case that sigma cannot be infinity, sigma is a finite value. Okay. So if you now substitute for J in the form of sigma E, Ampere Maxwell law becomes curl of H is equal to sigma, and electric field E is common in both terms, so I can actually put that outside. So I have sigma plus j omega epsilon into E. Okay. Now as before we take curl of Faraday's law, okay, to obtain del of del dot E minus del square E equals minus j omega mu curl of H, but I already know what is curl of H. Curl of H is nothing but minus j omega mu into sigma plus j omega epsilon into electric field E. Now we have Gauss's law which states that del dot D is equal to 0. We will continue to assume that D and E are related by a simple epsilon. Okay. So that is how we were actually able to rewrite del by del T of D in the form of j omega epsilon E. So we assume that D is equal to epsilon E, and moreover we still assume that del dot D equal to 0. So there might be cases of conduction current in an imperfect dielectric, but we will assume that at no point inside the imperfect dielectric surface there are some isolated free charges. Okay. So because of that, del dot D equal to 0 still implies del dot E equal to 0, and as such this term del of del dot E can be cancelled, can be made equal to 0. There is a minus sign to the right hand side, minus sign here on the left hand side, they can be cancelled each other, so that what you get is an equation for describing how the electric field E will change inside an imperfect dielectric, being given as j omega mu into sigma plus j omega epsilon times electric field E. As before, we will assume that electric field has only one particular component. So let us assume that electric field E is x component electric field, and it is a function only of z variable, right. So because the wave is propagating along z direction, so in our assumption, therefore this del square vector Laplacian can be replaced by del square by del z square times only Ex of z, okay, which is equal to j omega mu into sigma plus j omega epsilon times Ex. Remember, in the case where sigma was equal to 0, this equation was actually minus omega square mu epsilon, and we recognize that mu epsilon is nothing but 1 by v square, and therefore we wrote this as minus omega square by v square into E, and we call this omega square by v square as k square. So therefore we actually had a very simple solution for Ex, which was in the form of e power minus j kz, and k was a real quantity. This was for the lossless case or a perfect dielectric case, right. So this was the case of a lossless perfect dielectric, wherein the wave was actually going as a nice cosine wave whose amplitude was not really changing with z, in the sense that the amplitude of the electric field would actually remain constant, it would not change with as you go further. There is no change in the amplitude of the electric field, it was only propagating as a sinusoidal wave along z direction, okay, as you can see in this particular case. This was for the lossless case when sigma was equal to 0. However, now sigma is certainly not 0, and this quantity can still be written as some k square, except now that k must become complex, correct, because k square is equal to j omega mu into sigma plus j omega epsilon. However, k will then be equal to square root of j omega mu sigma plus j omega epsilon, okay, and because of this is obviously going to be a complex number. This complex number is usually split and written as alpha plus j beta, where we call alpha as attenuation constant or attenuation coefficient, okay, and this is usually measured in Nepers per meter. We call this beta as phase constant, and this is usually measured in radians per meter. So what is happening out there? We have an equation which is looking very similar to, at the left hand side is exactly equal to that of a lossless wave propagation, but the right hand side I have k square, which is actually a complex number, right. So k square is a complex number and k will be equal to alpha plus j beta. The solution of this equation would be that you have two waves, right, some Ex plus e to the power minus kz, because k is complex I cannot just write this as e power minus jkz, I have to write this as e power minus kz, plus there would be some backward propagating wave. Okay, this backward propagating wave could be generated by a source that is kept, or it could be coming off from some reflected wave. Okay, so if you don't want to really concentrate on the backward propagating wave at this point, we don't have to consider this one. We will simply assume that the wave is propagating along plus z direction and it is simply going out, okay, in that direction. Okay, now if you look at this expression that we have written here, you see that this is e power minus kz, but substituting for k in the form of alpha and j beta, you will see that this would be, so let us put a 0 subscript to indicate that this is amplitude measured at a particular plane. Okay, so you have Ex 0 plus e to the power minus alpha z e power minus j beta z, and if you want to find out what is Ex as a function of both z as well as time, you can then convert this phasor into a real time variable form. So you will get Ex 0 plus e power minus alpha z, I am assuming that this amplitude is still real, times cos omega t minus beta z, right. So this equation for the electric field component, right, of this plane wave propagating inside an imperfect dielectric is very similar to that of a perfect dielectric propagation, except that the amplitude is actually decaying as a function of z, right. So you see that this exponential minus alpha z is there, right. This would be something like, you know, a current decaying in that of a RC circuit, right. There we will also have a similar alpha there, or rather in terms of tau, the time constant there. So here we have an alpha. So when z becomes much larger than, as z increases, the corresponding value of e power minus alpha z actually starts decreasing, and therefore the amplitude starts decaying. So if you actually plot the amplitude alone or the magnitude of the electric field alone, you would find that, right, this would be the magnitude of the electric field that you are plotting, and you would find that at z equal to 0 it would have the value of Ex 0 plus, okay, and beyond that it would have a value that is coming through this. But as z increases, right, as you move away from the source, you will see that the amplitude actually starts decaying with a slope of alpha. Okay, so the initial slope of this line would be alpha, and this alpha tells you the rate of decay of the amplitude of the electric field. Okay, so this rate of decay of amplitude is measured in Nepper per meter. Sometimes this alpha, or actually most of the time this alpha attenuation coefficient is actually given in terms of dB per meter or dB per kilometer. Okay, and there is a nice conversion between Nepper per meter to dB per kilometer, something that I don't have enough time to discuss that, but you can actually take a look at the textbook to see how to convert from natural units of attenuation coefficient in the form of Nepper per meter into the more practical units of dB per meter. Okay, and you can use this one and you can see how the amplitude is actually changing. The point is, amplitude changes or amplitude decays exponentially as you move away from the source. Okay, so the lesson that we need to learn is that in an imperfect dielectric, J is not 0. Okay, in fact J will be equal to sigma E, and this won't be equal to 0. The second lesson to learn here is that the waves actually attenuate, right, as they begin to move along z. Okay, if they are very far away from the source, then the value of the wave would still be oscillating with the propagation constant of beta, right, or with a phase constant of beta. So this beta, which tells you how the phase is changing as the wave propagates, that would still be there. Okay, except that the amplitude actually starts decaying exponentially inside that of a imperfect dielectric. Okay. So far what we have looked at is propagation of wave inside an imperfect dielectric, and we have seen that this k, which is the propagation coefficient or the propagation constant, is actually complex, consisting of real part and imaginary part, the real part being the attenuation and this imaginary part giving you the phase change or phase shift of the wave as it propagates through the material medium. Okay. There are a couple of cases that we can consider at this point, okay, which will tell us the relative magnitude of sigma and omega epsilon. First consider the case where sigma is much larger than omega epsilon. Okay, this would be the case of a good conductor, that of a metal for example. Okay, you take copper or gold. Okay, so these metals will have a large conduction current, okay, compared to a small displacement current. Therefore, one can make this approximation of sigma being much larger than omega epsilon, and when you put that back into this expression for K, you will see that K is equal to square root of j omega mu sigma. Okay, this can be rewritten as, by taking the square root of j, can be rewritten as omega mu sigma by 2. Okay, this square root actually covers everything, and then there is 1 plus j. If you are not convinced with this one, you can actually take a simple couple of seconds to convince yourself. What you want is root of j, right? So root of j is nothing but square root of e power j pi by 2, but this is nothing but e power j pi by 4, which is 1 plus j by root 2, because e power j pi by 4 is cos pi by 4 plus j sin pi by 4, and cos and sin pi by 4 are equal to 1 by root 2. So this root 2 goes into this omega mu sigma. Okay, but I also know that omega is equal to 2 pi f. Therefore, I can write this K as 1 plus j into pi f mu sigma under root. Okay, so clearly in this case what we have is alpha being equal to beta, both given by pi f mu sigma. Okay, so what will happen to the electric field that is propagating? Well, the electric field will be Ex of z given with some initial amplitude Ex0, I am assuming still only forward propagating wave, and then you have e power minus alpha z, e power minus j beta z. So both of these are equal to square root of pi f mu sigma, but rather than talking in terms of alpha, okay, for a case where you are considering a good conductor, you will actually introduce a different quantity called skin depth. Okay, skin depth is given by 1 by alpha, and since alpha is given by square root pi f mu sigma, the skin depth delta, okay, let me write this down this as, and say this is skin depth delta is given by 1 by square root of pi f mu sigma. So because of this, the electric field propagation inside a good conductor is equal to whatever the surface value that you have, or whatever the initial amplitude Ex0 that you have, times e to the power minus 1 plus j z by delta. Correct? Its amplitude is going as e power minus z by delta, and its phase is changing as e power minus j z by delta. Okay. Now we will not discuss about the phase, because phase only changes, phase is not very important at this point, but what we are interested is to see what will be the behavior of this e power minus z by delta. Okay. So you have e power minus z by delta, and if z is around say 4 or 5 delta and beyond this one, right. So if this z becomes greater than 4 or 5 delta, that is as the wave propagates, if you propagate for more than 4 or 5 delta, then the amplitude would have decayed to less than or equal to 99% of Ex0. Okay. So this is how the amplitude would have actually decayed, right. So this decay, if you look at this, this is about 4 delta or 5 delta. Okay. So 4 delta or 5 delta along z, the amplitude would have actually decayed by 99%. So which means that the value at this point would only be about 1% of Ex of 0. Okay. So this was not, this would have decayed by 99%, and therefore this would have been around at 1%. Okay. This would happen for 4 delta or 5 delta. That is why this rule of thumb which says that 5 delta units is sufficient for the wave to have been decayed. So the wave would just decay and become very small compared to what its value at surface is. Okay. Alright. So this is skin depth. We will come back to skin depth and some of its ramifications very shortly. Let us for a minute consider the other case around. Okay. We will come back to skin depth in the next module. So for now, let us simply consider the other extreme situation where sigma is much smaller than j omega epsilon. This would be the case where it is a very good dielectric. So this is a very good dielectric that I am considering, but there is some amount of loss. Okay. So there is some small insignificant conduction current, which we can neglect in the form of j omega epsilon, I mean in terms of the displacement current. So what will happen to k? K will be square root of j omega mu j omega epsilon, which will give you j omega square root mu epsilon, right. This would be equal to no attenuation and full phase constant. Okay. This would be very similar to, this is exactly similar to that of the lossless case. Okay. So in the lossless case, or in the very good dielectric, if we can neglect the conduction current, then the propagation constant will be imaginary, right. K will be equal to j beta, and the wave will only suffer phase shift as it propagates through the material, and there is no change in the amplitude. Okay. It is also interesting to look at what would be the impedance eta, right. I already know from Faraday's law that minus j omega mu h will be equal to curl of electric field, right. So therefore h will be equal to minus 1 by j omega mu curl of electric field. If I assume that electric field E is along x, right, and it is going as e power minus alpha z e power minus j beta z with some initial amplitude of Ex 0, right. If this is how the electric field E is going, then h will have only y component, and this will be given by h is equal to y hat, and then you have Ex 0 e power minus alpha z e power minus j beta z, but this curl of E, the y component is nothing but del Ex by del z. So I can actually differentiate this Ex by z, and I will get alpha plus j beta, which would be minus sign here, okay, and then divided by j omega mu, correct. So this is what I get. There is already a minus sign, therefore the two minus signs will cancel and you are going to get away from this one. This is nothing but the electric field vector itself, right. This is nothing but the electric field vector E. Therefore this H will, which is given by E into alpha plus j beta divided by j omega mu, can be written in this way, and therefore this fellow should be in the form of a impedance, right. So E by H is impedance, therefore the ratio of the electric field to magnetic field in the case of this imperfect dielectric is given by j omega mu divided by alpha plus j beta. Alpha plus j beta is nothing but k, and k is nothing but square root of j omega mu into sigma plus j omega epsilon, and this can be further simplified and written as j omega mu in the numerator divided by sigma plus j omega epsilon. You can convince yourself that this expression must be true, because when you take sigma equal to 0, this ratio of E by H, which is basically the ratio of the electric and magnetic field vectors and describes the impedance, right, wave impedance, will actually reduce to mu by epsilon, and for the case of free space this will be equal to square root of mu 0 by epsilon 0. So this actually equation is correct, and that actually checks out with the case that we already know how to compute the wave impedance. But there is actually a significant thing that has happened over here. For the lossless case, eta will always be real, indicating that electric field and magnetic field are in phase with each other. They actually carry some amount of energy. Whereas in this case, eta is complex, indicating that E and H are not always in phase with each other. In fact, there is the phase between the two is not 0, indicating that there is some loss in the power. So the entire power is actually not being able to be carried because eta is not real, indicating that E and H will have some amount of phase difference between that, and only the power of the order of cos of that phase difference will be carried by the wave. Okay. So this loss is inevitable because of the imperfect dielectric or a good conductor that we have assumed.